Okay, so we spent a couple days or so going over delta H's of essentially just a heat transfer from one thing to another, and those are the enthalpies between the breaking and the reforming of bonds or the transference of the energy. I want to talk now about how that's going to help us with reactions in general. And there's going to be, I'm just going to point out, we're going to do a lot of stuff to end up with a shortcut. So get ready to just groan about this in just a moment. But I want you to see how we get to do what we get to do. So now let's look at heat of formations. Oops, I need to get my participants up here so I can drag them over and you guys can be my far right hand ruler. Okay, so let's do heats of formation. These will be delta H naught F for forming. Now, when we look at this little moniker right here that we're going to call the delta H naught of formation, remember that there's some good stuff in here. Remember that naught means 1 mole of substance. And the F means to form it. Now, this is where we are going to do something that I told you we will never ever do, except this once. Check it out. You guys remember this? Good old fashioned, let me go ahead and do that in purple just because. Let's do hydrogen plus oxygen. What are we going to make? That's right, water. Now here's where it gets kind of fun. In the past, we would normally balance this as we'd balance this as 2 hydrogens, 1 oxygen makes 2 waters. We're not going to do that because this naught means that we have to do it for only 1 mole. So if we're going to figure out how much energy it takes to make that water, we're actually going to have to put a 1 here, which means that's going to have to be a 1, which means the water has to be a 1/2. Ooh, something we've never done before. In thermodynamics, because we define the naught, as it were, a standard conditions, because it's on a 1 mole, that means everything else can be fractional now. So unlike the balances before where I said we won't use fractions, we absolutely have to now in order to maintain that 1 mole of substance. Now this has a delta H naught of formation equal to negative 241.8 kilojoules per mole. We'll be using this one in carbon dioxide quite a lot here, so we'll get used to these numbers here. Now, as we look at that delta H naught being a negative number, what does that mean? Ben, what does that mean, negative?
Losing energy.
Right, it is exothermic, it's giving it off. All right, so the reason why they come together in the first place is that the energy inside those bonds for the water are less than the other two. It'll give it off as it comes, as they do the reaction, and exothermic. And Mother Nature likes to do this, so that's a good thing. Carbon plus oxygen goes to make CO2. This has a delta H naught of forming equal to negative 393.5 kilojoules per mole. So when you get carbon and oxygen together, They'll make carbon dioxide and it will give you energy. This is essentially burning coal. This is exothermic. Now, if you notice, this is always here starting with elements to make the compound. So note, delta H naught of formation is the enthalpy of forming this compound. And here's the kicker, from the elements. And so while making water or making carbon dioxide is kind of a no-brainer, right? We see that we have elemental hydrogen, elemental oxygen, elemental carbon, elemental oxygen. What happens if you're making something that is slightly more complex? What if you're making ethanol? What if you're making C2H5OH? Well, our ingredients are going to be carbons, hydrogens, and oxygens. I know it's kind of a little weird, but this is how this stuff is defined. If you take things from their elemental state, how much energy will you get out or need to do it? Now, again, here we see that we would have 2 carbons, 3 hydrogens, and our mystical magical 1/2 oxygen in order to make that 1 ethanol. So by defining these delta H naughts of formation, we're able to take compounds and build them from their elements, whether we're making water or carbon dioxide or ethanol. But what happens if you're not doing that? What happens if you're actually going from compounds to compounds to compounds? Because that's in reality what we do. So what if so actually I should say, so these are making 1 compound from the elements. So they're just making 1 compound from the elements. But what if you form a compound from other compounds? Most of the chemical reactions we do are not centered around starting out with elemental things. I mean, water and carbon dioxide, you can clearly see that, but it is already starting to look weird making alcohol from a bunch of soot, hydrogen gas, and oxygen gas. It kind of doesn't make sense. What it's usually done is you take other compounds to make these things. So consider this guy. We have C2H4 plus 3 oxygens goes to make a couple of carbon dioxides and a couple of waters. Now, the delta H of this reaction overall, now notice that this gets a little weird. The delta H of the reaction is equal to -414 kilojoules per mole. But from this, we could actually use information we already have written above to figure out, well, how much energy is actually stored up or inside of this C2H4. So let me get that in black. Actually, I'm not going to ask the question. I'm going to say we can use this information with the info above to get the delta H naught of formation for C2H4. Okay, if we want to figure out just how much energy is in this guy right here, we can look at all the other constituents, because hopefully you guys have already figured out, or at least made the mental leap, that if I am taking parts and summing them up for a whole, and other parts and summing them up for a whole, then the sum of the sums should equal the whole thing. So what I'm going to do is, since I already have above carbon dioxide, I already have water, I'll talk about oxygen in a second, the sum of all these parts here plus the phantom part here of the C2H4 should end up to the overall H for the reaction. So the parts should all equal the whole.
Oh, Mr. Colby? Hi, it's Maddie. Good, how are you?
Doing okay.
I'm calling because there was an issue with the insurance coordinator at Dr. Jeanette's office.
Well, there's no more problems now. Okay. So what do we need? We need some reactions. To get C2H4s, oh, I should say, that's a bad way of writing that. To get the delta H naught of formation of C2H4, we need a system of equations. First, I want to know how we get C2H4 in the first place. How do we get ethylene in the first place? For C2H4, let's form it. We had carbons and hydrogens go to make C2H4. Hopefully we see that there'll be 2 carbons and 2 hydrogens straight away. Now, we also have carbon dioxide up there. So as we wrote before, we have a carbon and an oxygen, goes to make CO2. And we also have the water. That's now hydrogen plus a half of an oxygen, goes to make H2O. Now, what about O2? Okay, so what are we going to do about oxygen? How do we write an equation for oxygen being formed from its elements? Kimchi, what do you think?
I'm thinking that, well, does it have to do with how O2 like stays as 2 O's?
It has everything to do with the fact that we are asking, and this is where I love doing this, and I'm glad you're like, wait, it can't be this. It is this. Watch this, Kimchi. What do we have up here? We are going to make ethylene. Okay, how do you make ethylene? From carbon and hydrogen. Check.
Yes.
Yes. Just say yes, Kimchi.
Yes.
Now we're going to make carbon dioxide. We can make that from carbon and oxygen, yes?
Yes.
Now we're going to make water. We can make that from hydrogen and oxygen, yes?
Yes.
Now, how do we make oxygen?
from oxygen.
So then, where's Garrett? What would that imply about things on the left and right? They would cancel each other out. So it's interesting. You can't form an element from an element. It's already itself. So you cannot form an element from itself. It just is. And so even though it's an ingredient there, we'll find out that it, as far as making its own contribution, it doesn't exist. So we have three equations up here, and what we want to do is we want to make C2H4, okay? So here we go. If we want delta H naught of formation of C2H4, we need to arrange the equations such that they match what we want. What do I mean by this? Okay. So we started out with the equation that was, and let me go ahead and, well, I'll leave it in blue. C2H4 plus oxygen goes to make CO2 and H2O. And there were a couple of waters and a couple of carbon dioxides and I think 3 oxygen. Okay, but we want to make ethylene, not consume it. So let's switch the equation. Let's reverse it. You'll see why in a second. If we reverse that reaction, we are going to now have 2 carbon dioxides plus 2 waters going to make C2H4 and 3 oxygens. Now, you make that nice and pretty. Now, I want to point out something here. The delta H of this reaction is going to have to change. How is it intuitively going to have to change, Ben?
Would it change by the inverse?
Yeah, right? If going forward released energy, then going backward must take it. So when you flip a reaction, you flip the sign. So that's now positive 414 kilojoules per mole. I'm going to actually just go to the next line because I don't trust this. All right. So this delta H of the reaction now is positive 414 kilojoules per mole. That means you'd have to do something to make this go. When you flip a reaction, you reverse the sign. Okay. Now, why have I done that? I've done that Because if we take a look up here, we have other equations involving the carbons and the hydrogens, and watch the magic. We're going to try to get this guy. We're trying to get the C2H4 all by itself. So, and I know it's going to kind of get in the way here. Actually, let me see if I can move these. Let me see if I can move them just a little bit so I can manage this. Do that. Oh, there we go. Okay. So if I have that one right there, let's look at what I can do with the other ones. If I now do 2 carbons plus 2 oxygens goes to make 2 CO2s. Oh, and I want to keep this red, actually. Now, why did I go ahead and multiply everything by 2? Well, because in our reaction, where'd it go? In our reaction, we had 2 carbon dioxides. So I'm trying to get to where I can make it look like the equation that we want, which is going to be this guy right here. But I have to be using our original equation where we had the 2 carbon dioxides and the 3 oxygens and the 2 waters. So what we're doing here, this again is, some people have said it's kind of like mechanisms again, just make sure it works. So I'm doing 2, which means I now have to figure out what happens to my heat of reaction. Now, if you guys remember, I've now doubled the amount of stuff. Look at the units on the delta H of the reaction. They are kilojoules per mole. And so when I do this, and in fact, by the way, this is not a reaction. If we notice, we are forming something. We are forming something from its elements. So this is the delta H naught. Now, I am going to say delta H naught of formation. We have that number of negative 393.5 kilojoules per mole. But since I now have this 2, so I have twice as many stuff, I'm going to have to multiply this by 2 as well. I have twice as much stuff, I should get twice as much energy. All right, along the same lines, I'll do the same thing with the water one. So I have 2 hydrogens plus an oxygen goes to make 2 waters. Again, that is to go and match up with the equations above. We were told that that was a delta H, and now again, this is a knot. We're making an element, or I mean a compound from its elements. So we're not talking about a reaction, we're talking about the reaction of forming it from its elements. That was negative 241.8 kilojoules per mole. But hopefully you guys see that since I multiplied everything by 2, I should multiply that by 2. Now, at the end of the day, taking all of these reactions and looking at it, look what happens here. I've got, let's see if I can do this really light, 2 carbon dioxides, cancel 2 carbon dioxides, 2 water, cancel out 2 waters, and I've got 1, 2, 3 oxygens. Oh, look.
Forrest, I have a question.
Nope.
Wait, did he lag out?
This happens sometimes. It's possible.
He cut off for like a good 30 seconds for me.
Yeah, we lost him, guys.
Oh god.
Oh.
Lecture
long
lecture.
David, why don't you just speak? Boris ain't here. How's life?
Kimchi, you want to lead the class?
Doing what?
Give us a thermo lecture from, like, I don't know, Smart Person College.
Smart person college. I mean, no, it's okay.
I talked to Log yesterday.
Did you?
Yeah, he called me.
Cute. Talia's coming home.
You not home already?
No, she's been like living in Denver with her friends.
Oh. I assume she'd be home.
Yeah, you would think. She sounds like she's pretty upset about it, but she's coming home anyways. Is this recording? Yes.
Okay, go ahead.
So my internet just took a massive dump. I just called my guys and they didn't even like pick up. It just goes, yeah, we got it damaged and somebody's out there trying to fix it. I have no idea when it's going to be fixed. So at this point, whoever happens to be the host might as well just stop recording. When it gets fixed, I will try to send a thing and get whoever I can to join in. But I have no idea when they'll fix it, guys. I'm sorry.
How do we stop the recording?
You can relay them to me, or you can put it up on